And go ahead, Kyle.
My name is Kyle Tibbetts. I'll be talking about the 2002 Nobel Prize laureates Raymond Davis Jr. and Masatoshi Koshiba. They both received a quarter of the prize for their contributions in astrophysics, but more particularly for the detection of solar neutrinos. So Raymond Davis Jr. received his PhD at Yale. However, he got his PhD in physical chemistry, not physics. But in 1948, he worked at Brookhaven Laboratory, and he was told by his supervisor to go to the library and choose any topic he wanted. So he found a paper written on neutrinos, and he decided to set up an experiment to find if neutrinos are actually the source of hydrogen fusion in the sun or nuclear fusion. Masatoshi Koshiba graduated from the University of Rochester in 1955. He received his PhD in physics, and he wanted to expand upon Davis's experiments by using more sensitive materials and better detectors. So first of all, what are neutrinos? Well, according to the standard model, there are three different neutrinos. There's the electron neutrino, the muon neutrino, and the tau neutrino. The first thing that most of us probably know is that neutrinos are neutral, so they don't have a charge. Also, according to the model, they're massless, which means that they travel at the speed of light. So before Davis performed his experiments, John Bacall, a mathematician and a theorist, calculated the amount of neutrinos released from the sun. So the first thing we want to look at is the proton-proton chain. And he calculated that there are about 10 to the 11th protons or neutrinos per second per centimeter squared released from the sun. So in other words, every second there's trillions of neutrinos bombarding us as well as Earth. These are really important because they are the main source of hydrogen fusion within the sun, but they're very hard to detect because they exist at really low energies. So what Davis wanted to do was look at boron decay, although not as abundant, but existed at a variety of energies. So what's interesting about boron decay is that it releases a neutrino, and this particular neutrino is highly energized, and in fact it has high enough energy to excite chlorine in its ground state and produce argon in its excited state as well as an electron. So what Davis did was he set up a lab in Homestake, and this was a mile below ground, and he used a 100,000 gallon tank of solvent, dry cleaner solvent, which had a lot of chlorine in it. So he wanted to use this experiment or this formula, and he can't detect neutrinos directly. So what he did was he said, well, neutrinos are constantly hitting us, so they're going to go to my tank and interact with chlorine. However, even though there's trillions of neutrinos, this reaction is pretty rare. So John Bacall calculated that there's going to be about 8.6 solar neutrinos per week that are interacting with chlorine. Now, Davis couldn't do get his results every week. He had to wait every couple of months. This is because the half-life of argon is about 35 days. So this kind of put a hurt on Davis because he had to wait every couple of months to get his results. He couldn't do it instantly. So what did he get? Well, he performed this for nearly 25 years, and throughout each result, he was getting consistent answers. The scientific community doubted Davis's results. On average, he got about 2.5 solar neutrino units per week, which is about one-third of the calculated results by John Bacall. So what does this mean? Well, Bacall knew that his calculations were 100% correct. Davis knew that his experiment was 100% correct, so there had to be a problem here. But what was his problem? Well, Davis said, well, maybe there's a solar neutrino problem. And basically what that says is that there's three different flavors of neutrinos, and at any instant, these neutrinos could oscillate to a different neutrino. Unfortunately, Davis's experiment wasn't sensitive enough to detect the oscillations. So then came along Koshiba. He performed experiments throughout the 80s at the Kamiokande lab in Japan. But the most important one is the super Kamiokande, which is this one we're looking at. So what he did, instead of using chlorine, he used ultra pure water, and he built this still underground, only 1,000 meters. And again, the reason why it has to be underground is because you want to deflect all cosmic rays and background noise reaching the detectors. All you want is just neutrinos. So the reason why I used water instead of chlorine is because it turns out neutrinos could react with water. So the neutrino comes in, hits the water, it could interact with an electron, and once it interacts with the electron, it releases a highly energized particle. This highly energized particle travels faster than the speed of light in water. So ordinarily, the speed of light in water is 0.75 times the speed of light. This is slightly faster. So what happens is it basically creates a sonic boom of light, not sound. So this is called Cherenkov radiation, and that's caused by a particle traveling faster than the speed of light. So what this happens, once Cherenkov radiation is released, a ring of light is projected on the photomultiplier tubes. And based on the sharpness of this ring of light, Koshiba was able to determine what type of neutrino he was looking at. Now what's really important about this experiment is that unlike Davis, where he had to wait 2 months to get his results, Koshiba could get them instantly. So what did he get? Well, first of all, he was only able to detect 2/3 of the calculated value of Bacal's results. So is there a problem here? Maybe, but probably not. So because he was getting real-time results, he was able to get the direction of the neutrinos. So the first thing we want to look at is the sun, because that's what Davis's main experiment was, to see if hydrogen fusion is the main source of energy from the sun. So it turns out from the Koshiba's results, the direction was actually coming from the sun. So he confirmed that Davis's neutrinos were coming from the sun. Also, though, there's neutrinos coming from the Earth, from the other side of the Earth, that are traveling to his lab. But the thing is that he was only getting 1/2 the expected value down here. So that poses another problem, according to the standard model. But Koshiba said there has to be something wrong with the standard model. So remember that neutrinos travel at the speed of light, but if they travel at the speed of light, they can't oscillate like Davis predicted. Because in order to oscillate, they need to change. In order to change between flavors, you need time. But if you're traveling at the speed of light, time doesn't change. So how is it that these neutrinos are changing? So it turns out that the neutrinos actually must have mass in order to change between flavors. So he said, well, neutrinos don't have charge, so the only difference between these neutrinos coming from here and these ones coming from up top is the time it takes for them to hit the detector. So although he's getting half the results, that's because they're at different flavors. So turns out that Davis, the neutrinos he was detecting from the sun, were only electron neutrinos, so 1/3 of the total amount of neutrinos. The neutrinos that Koshiba detected were electron neutrinos as well as muon neutrinos, or 2/3 of the expected results. So based on both of their experiments, they confirmed that the sun produces energy as predicted through hydrogen fusion, not previously thought back in the 40s through gravity. Also, they modified the standard model, stating that neutrinos must have mass. If they are massless, then they can't oscillate, and then they don't exist. So they have to have mass. And finally, everything has an antiparticle. So if you think of an electron, its antiparticle is a positron. So its anti is the opposite charge. But neutrinos, they're neutral, so they don't have an opposite charge. So it's believed that antineutrinos share similar characteristics as neutrinos, but we don't quite know exactly what the antineutrinos are yet, or how they're characterized. Any questions? tau neutrinos? Good question. So in 1999, Snow Observatory in Canada designed an experiment that was 2 kilometers below ground, and it was similar to Davis and Koshiba's experiments, except they used deuterium, which is heavy water. And it turns out that they were actually able to detect all 3 of the flavors. They did this over a period of 19 months. They got 2,000 interactions between neutrinos and heavy water out of 10 billion trillion total amount of neutrinos that actually went through. Any other questions?
Any questions? Guess not. Okay, thanks.